In this experiment, we are validating the form of Newton's second law. In its original form, it looks like this. In the first part of the experiment, where we are keeping the mass constant, it should be obvious that we expect a straight line if we have force values on the vertical axis and acceleration values on the horizontal axis. In that case, we would expect the slope to be equivalent to the mass that was kept constant. To determine the acceleration values, you will be collecting initial and final velocity values as well as the time to reach final velocity. We can then use the definition of acceleration. Acceleration is equal to v final minus v initial over t. In this case, the initial velocity will be 0 and the final velocity and time values can be gotten from the simulation to put in the first data table. You can have Excel complete this calculation for you if you copy just the final velocity column and the time column into Excel and include the equation in each cell of the acceleration column. Then copy the force column next to your acceleration column so that Excel plots the force on the vertical axis and acceleration on the horizontal axis when you choose those two columns for graphing. You should verify that the slope is your constant mass by checking its units. Recall the definition of slope is equal to the change in y over the change in x. To check that your slope is equivalent or close to your constant, put the units of what is on the vertical or y-axis in the numerator and the units of what is on the horizontal or x-axis in the denominator. In this case, that would be newtons divided by meters per second squared. Replace Newton with its equivalent combination of units and see if you get kilograms out of this division. For the second part of the lab, the mass will change for a constant applied force on each mass. Velocity and time values will be collected for each run to calculate the acceleration. You can copy this data into Excel and have it calculate your acceleration. Beside the acceleration column, you would want to put the mass column. Excel can then be used to plot acceleration on the horizontal axis and mass on the vertical axis. When it comes to graphing, if you have something other than a straight line, then it is possible that it will lend itself to some type of curve. If you're plotting against positive powers of the variable, you get parabolas, you can get curves that approach the asymptote, all sorts of stuff like that. We plot graphs to find out the relationship between the variables that we think are related. If the initial graph is curved, then we try to linearize it to try to discover what the relationship between those variables that led to the curved graph might be. A linearized graph that we get by raising one or both variables to some power, positive or negative, can help to write an equation based on those variables that can be evaluated in later experiments. For the data from part 2, it may be that the plot of the data is not linear. We can understand why if we go back to Newton's second law and manipulate it to match what is graphed. To match up, it is necessary to divide both sides by the acceleration, isolating the mass. A graph of the reciprocal of a variable is indeed a curve. If the fit chosen to fit the data is a power fit, then the equation provided by Excel clearly shows that the best fit is to have the horizontal variable represented by a reciprocal. This can then tell how to linearize this graph. If you open a column between the acceleration and the mass, you can let it be the reciprocal of your acceleration values. Excel can calculate these for you. A new graph made of these reciprocal acceleration values and the mass should now be linear. Check the units of your slope to see if it is consistent with what is expected. Part 3 goes back to plotting force on the vertical axis and acceleration on the horizontal, but this time a net force will be involved that will include friction. This should lead to 3 additional graphs. And as with the previous 2, you should check the value and unit of the slope to what is kept constant. One outcome of increasing the friction may be a reduction of data points to be plotted. Since you are to plot force versus acceleration, if there is no acceleration, then you have nothing to plot. Only plot data pairs of net force versus non-zero values of acceleration. The reason for the reduction of data pairs is the need to overcome static friction as the friction is increased. For the purposes of this lab, you need to overcome the static friction first by applying enough force to do so, but then back off a bit to accelerate the mass. What should be submitted for grading? The data tables and answered questions, followed by at least 5 graphs, including a graph of anything that turns out to produce a curve when plotting the original data. All linear or linearized graphs should have their fits projected to the y-intercept and include the equation of the fit provided by Excel. The calculation sheet, where you demonstrate how you validated that the slope represents that which you kept constant for each of the data collection runs, should also be included.